Let's get started with the second talk. So the speaker is Elli, and she will tell us about generating Calabi-Yau manifolds from genetic algorithms. Please start.
Okay. Hi, everyone. Just to introduce myself before I get started, my name is Elli. I'm a PhD student based in London. And today I'm going to be talking to you about a project we finished a few months back, generating Calabi-Yau manifolds with genetic algorithms. So this is a project I did with some wonderful collaborators who I should give a shout out to, Per, Yang, who's my supervisor and one of the organizers of this conference, and Ed, Vishnu, and Andre. So of course, please do ask as many questions throughout the talk. It makes it more interesting for everyone involved, I think. So a quick outline of what I'm going to be talking to you today about. I'll first of all introduce some motivation as to why we even care about Calabi-Yau manifolds in string theory. Although I know this is a theoretical physics audience, I don't think I should spend too much time on this. Then I'll talk about the background of the mathematics. So I'll explain to you how you can construct these Calabi-Yau manifolds as hypersurfaces and toric varieties. And then I will talk to you about genetic algorithms. So I'll introduce what these are, and then talk to you a little bit of detail on the specifics of our genetic algorithm. And then I will show you the results. And finally, I want to talk a bit about the future directions, because this project is very much like a first step. It introduces this new approach of dealing with large numbers of Calabi-Yaus in string theory, but there are many ways that we can go from here. So yeah, very briefly, string theory is a theory that's only self-consistent if we have 10 dimensions of space-time, 1 dimension of time, and 9 dimensions of space. But of course, we live in a world of 3 dimensions of space. So compactification is one way we deal with this in string theory, where the extra 6 dimensions are curled up on some small compact manifold. And then the 10-dimensional background manifold is a direct product between the usual 4-dimensional Minkowski space and this compact manifold X. And then we have some conditions that we impose on this manifold. So first of all, in order to have unbroken n equals 1 supersymmetry, we require that the holonomy group of our manifold is SU3. And in order to be self-consistent with general relativity, to satisfy the vacuum-Einstein equations, we require that our manifold is also Ricci flat. But a Ricci flat manifold with holonomy SU3 is precisely a Calabi-Yau manifold, and this is why we're so interested in these manifolds in string theory. And you may have seen definitions of Calabi-Yaus in other ways, with trivial canonical bundle or vanishing first Chern class, but all of these definitions are somewhat related to each other. So there are 2 big problems in compactification in string theory. The first problem is we don't know one Calabi-Yau. We have lots and lots of potential Calabi-Yau manifolds that could describe the geometry of the extra dimensions. So this is what we refer to as a string landscape. And in fact, there is not even a proof that the number of Calabi-Yau manifolds in any given dimension is finite. It's believed to be so, but there is no proof of this. And so there's far too many of these manifolds to go through by hand and check each one and say, this one is suitable, let's keep this one is not suitable, let's get rid of this one. And by suitable, I mean that it would give rise to sensible physics in the low-dimensional effective field theory. So there's too many to definitely go through by hand, and there's even too many to go through exhaustively on a computer and check each one. So this is one area where machine learning can help us. So we can use machine learning to identify regions of the string landscape that give rise to standard model-like physics. And then the second problem is that even if we know the correct Calabi-Yau manifold, we also need the Ricci flat metric in order to compute the particle content of the effective field theory. But there's no method for computing the analytical Ricci flat metric on a given Calabi-Yau. There are some numerical methods, but these become very, very expensive. So this is another area where machine learning is being used quite a bit now, is to engineer approximations of the metric using things like neural networks or other machine learning algorithms. So I'm not going to talk to you today about metrics. I'm going to focus more on this first problem. And what I'll show you is that we can use machine learning algorithms to specify properties of the Calabi-Yau that we after that would give us sensible standard model-like physics. And then we can use the machine learning models to generate examples for us. So there are many ways to construct Calabi-Yaus. You can do them as surgeries or fibrations, but the method that I'm going to focus on today is a construction of a Calabi-Yau manifold as a hypersurface in a toric variety. So very briefly, algebraic varieties are geometries described by the solution set of a system of polynomials. And then toric varieties are simply a special kind of algebraic varieties where you have the torus as a dense open subset and the action of the torus extends over the space. So I don't want to focus too much on the toric geometry, but what I do want to stress is that you can construct toric varieties from polytopes. So polytopes are just the convex hull of a set of points in a lattice. And then from a polytope, you can construct a fan, so a collection of cones. So each face in the polytopes, each edge in this 2D polytope gives rise to a cone in a fan. And then from each cone in our fan, we construct an affine toric variety, and then we glue these together to create our total toric variety. So what Batyrov and Borisov discovered in the early 90s was if the polytope that you start with is a so-called reflexive polytope, and I'll define precisely what I mean for you in a second by reflexive polytopes. But yeah, if you start with a polytope that's reflexive, it follows that the resulting toric variety is such that if you take any generic anti-canonical hypersurface in this toric variety, this is a Calabi-Yau variety. And in general, if you start from a polytope and you get a toric variety, these are going to have, if you start from a reflexive polytope, you're going to have a toric variety with at most Gorenstein singularities. And the Calabi-Yau hypersurface inherit the singularities of the ambient space. So we would like a smooth ambient space and a smooth Calabi-Yau. So we want to resolve our singularities. And the way we do that is we take certain triangulations of our original polytope. So I won't talk about this until the end, but one of the future directions we're going to look at now is doing triangulations of our polytope. So, as I said, a polytope is the convex hull of a set of points in a lattice. We say that a polytope is a lattice polytope if all of its vertices, so the red dots here, lie on integer lattice points. And we say a polytope satisfies the IP property if it contains a single interior point at the origin, so these blue dots here. And then the dual of a polytope is defined for you here as the convex hull of a set of points in the dual lattice, such that the pairing between all points in the original polytope is greater than or equal to -1. So a polytope is defined to be a reflexive polytope simply if it's a lattice polytope that satisfies the IP property, such that its dual is also a lattice polytope that satisfies the IP property. So yeah, here is a dual pair of reflexive polytopes in 2 dimensions. We have vertices on lattice points and we have one interior point at the origin. So that's one definition of a reflexive polytope. But we have another equivalent definition of a reflexive polytope, which is defined in terms of the hyperplane representation. So there are usually 2 ways to represent a polytope. You have the vertex matrix representation, where the columns of your matrix are the vertex coordinates of your vertices. And then we have the hyperplane representation, which is given by a set of hyperplanes. So polytopes also described as the intersection of half spaces. So each face in your polytope describes a hyperplane, and this hyperplane describes a half space, and then the polytope is simply the intersection of all the half spaces. So here we see the definition in terms of the hyperplanes. The AIs are the distances of the hyperplanes from the origin, and then the UIs, these are some primitive lattice vectors in your dual lattice. So if we're given a polytope described in its hyperplane representation, then we can define a polytope to be reflexive if and only if it satisfies the IP property and if all of its hyperplanes lie at a distance 1 from the origin. So that means all of the AIs here are 1. So motivated by Batyrov and Borisov's discovery that we can get a Calabi-Yau manifold from a reflexive polytope, in the late 90s, about 5 or so years later, Hodge and Skarka developed an algorithm to completely classify all of these reflexive polytopes in any given dimension. So the algorithm, it consists of 2 steps. Firstly, you construct a set of maximal polytopes such that every reflexive polytope is a subpolytope of a maximal polytope. And then the second step is you simply construct all subpolytopes of the maximal ones, and you check which ones are reflexive and which ones aren't. So it was already known at that point that there are 16 reflexive polytopes in 2 dimensions, but using this algorithm, Hodge and Skarka classified all the reflexive polytopes in 3 dimensions, and they found 4,319. And then after this, they then classified all of the reflexive polytopes in 4 dimensions. And now they found 500 million. And these 4-dimensional reflexive polytopes, these are the ones that give us Calabi-Yau threefolds, so the ones that we're interested in string theory, because an n-dimensional reflexive polytope will give rise to an n-1 complex dimensional Calabi-Yau. So if we study this sequence, we have 16 in 2 dimensions, like 4,000 or so in 3 dimensions, and then we already have 500 million in 4 dimensions. Yeah, question?
Yeah, so are these the number that found or the number that exists?
Found and exist.
Found and exist.
Yeah, so it was already known by that point that there are 16 in 2 dimensions. They found a completely classified, this is a total number, 4,003, and then 500 million in 4.
Because I'm stuck with your part of this version.
Mm-hmm.
Is there any significance to these numbers or?
I don't know from like a pure mathematical point if these numbers are particularly significant. They did a very like brute force exhaustive search of this. I don't know if there's any beauty behind those numbers, but maybe. Yeah, so if we look at the sequence, we have 16 and 4,000 and then already 500 million in 4 dimensions. So you can imagine that the total number of 5-dimensional reflexive polytopes is going to be an extortionate number. So there isn't a complete classification of the 5-dimensional reflexive polytopes, but Scarpa and Scholler did complete a partial database. And essentially, they just did this first step of the algorithm, and they constructed all the maximal polytopes, and they took the maximal ones that were automatically reflexive. Because it's not always the case that a maximal polytope is a reflexive polytope. So yeah, doing that, they have the data set of 185 billion. So later on, when I show you the data sets of reflexive polytopes that we generated with our genetic algorithm, it's these ones here that we're comparing to. And also these are all available online if you want to play around with them at all. So moving on now to the genetic algorithm side of things. Don't worry if you're new to machine learning. This algorithm, I think, is one of the most simple machine learning algorithms I've come across because it simply mimics the process of natural selection. So you start with a population of individuals. So for us, the individuals were polytopes, and we represented each polytope as a bit list. So that's just a list of 0s and 1s. So the first thing you do in the process is you rank your population based on some fitness function. Of course, the fitness function is going to be dependent on the problem you're considering. Because for us, we wanted to generate reflexive polytopes, our fitness function gives a score to a polytope based on how close it is to being reflexive. And I'll define precisely that fitness function in a second. The next step is you select fit pairs of individuals from your population and you breed them to create a new generation of offspring. And there are many ways to do both the selection criteria and the breeding process. But essentially, fit pairs of individuals are selected for breeding based on some probability distribution. And the fitter an individual is, the more likely it is to be selected for breeding. And again, there's many ways you can do the crossover, but if you're dealing with bit lists, as we were, there's a very easy way to do this, and it's just randomly select a position in the bit list of the 2 parents, and then exchange the bits up until that point. And this, so 2 parents, in that case, will give you 2 new offspring. Now you have a new population, and the last thing you do is you do random mutation. So for us, that meant just randomly selecting a proportion of bits in the entire population and flipping them. So a 0 becomes a 1 and a 1 becomes a 0. Now you're left with a new population, and then simply what you do is you repeat this process over and over again. And if you defined everything correctly, then your fitness function, or the average fitness of your population should increase over time. So as I said, we had individuals that were polytopes, and we represented our polytopes as bit lists. So let's consider an n-dimensional polytope defined as a complex cell of m vectors. So as I said, you can represent that in a vertex matrix form where the columns are the vertex coordinates. So to convert that into a bit list, what we do is we first flatten the matrix column-wise. Now we have a 1D list of integers. Then we're going to subtract a negative number min from every entry, and min is a parameter that you specify from the beginning. And this just ensures that every entry is positive. So now with our list of positive integers, we convert each of them into a binary number, And then finally, we just prepend each binary number with some zeros to ensure that they're all of the same length. And again, the length of the binary number is a parameter you specify at the start. So this means that the length of your bit list is the number of vectors, so the n times the dimension of the polytopes, n, times the length of the binary number. And then the environment is simply all possible bit lists. So because a bit can either be a 0 or 1, there's two possibilities. The size of your environment is going to be 2 to the power the length of the bit list. So it's easiest to see this with an example. So here's a very simple 2D polytope. You can see we've got more than one interior point. So this is not a reflexive polytope. And here is its vertex matrix. So the columns are the vertices. So in step 1, we just flatten this matrix. In step 2, we're subtracting min, and we specified min to be -3. So we're adding 3 to every entry. And then in step 3, we're turning each of these positive integers into a binary number. And then finally, in step 4, we prepend these numbers with zeros just to ensure that each binary number is of length 3. So this long bit list here is encoding this polytope. And I don't know about you, but I look at this long list of zeros and ones, and I don't immediately see that it's this polytope here. It's quite an unphysical representation, I think, of the polytope, which is why it's so surprising that genetic algorithm is so successful in finding these polytopes. We have a sort of unphysical representation of our data, and the algorithm itself is very, very simple. But yeah, even so, the genetic algorithm is successful at generating reflexive polytopes. So here is our fitness function. So as I said, the fitness function gives a score to a polytope based on how close it is to being reflexive. And if we go back a few slides, the second definition here I gave for a polytope to be reflexive in terms of its hyperplane representation is that a polytope is reflexive if and only if it satisfies the IP property and of all of its hyperplanes lie at distance 1 from the origin, so the AI is a 1. So it's this definition of reflexivity that we used to define our fitness function. So ignore for now this third term, and let's just focus on the first two terms here. So IP of delta is 1 if delta satisfies the IP property, and 0 otherwise. And then in the second term, we have a sum of the differences of the distances of the hyperplanes from the origin, and 1, divided by total number of hyperplanes to get an average. So this means if delta is a reflexive polytope, IP of delta is going to be 1 because we satisfy the IP property. And so the first term will vanish. And then also, if delta is reflexive, all of the AIs are going to be 1. So this second term is going to vanish. Now, this third term, we include it if we don't just want to look for reflexive polytopes, but we want to look for reflexive polytopes that also have a specific number of points. So just to be clear what I mean by points, so this polytope here, we have 4 vertices in red, but the origin counts as a point, so that's 5 points, and then also with these points on the interior of the facets also count. So we have 4 vertices, but 9 points in that polytope. So NP of delta here is the number of points of your polytope delta, and then NP0 is the desired number of points thereafter. So again, you can see if delta satisfies the condition, it has the desired number of points. This third term will vanish, and so the maximum fitness score is 0, but if delta is not reflexive or it doesn't have the desired number of points thereafter, you're going to have some negative fitness. As I said, oh, sorry, question? Yes, that's a good point. I should mention the weights. So because we always want to look for reflexive polytopes, W1 and W2 should always be positive. In fact, we just set them equal to 1. They can be fine-tuned if you want, but we found it works if they just were 1. W3 we set to be 0 if we don't care about the number of points. And then again, we just set it equal to 1 if we did. But in reality, you could fine-tune the weights. Yeah, thank you for the question. So as I said, fit individuals are selected from the population based on some probability distribution. And this is the specific probability distribution that we used. It's called the roulette wheel selection method. So capital P is your population, S is an individual in your population, and F of S is the fitness of your individual. F bar and F max are the average and the maximum fitness of your population. and n pop is the size of your population. And then we have alpha. This parameter is essentially just specifies by how much the maximum, the fittest individual should be selected over the least fit. Yes, so one of the last things I want to say in the methodology is that if you have polytopes described by their vertex matrices, you can have equivalences between polytopes. So let's just consider this vertex matrix here describing this polytope. Because the columns describe the vertices, you can imagine just shuffling the columns in your matrix and you're simply just relabeling the vertices. But if you take the convex hull, it's still describing exactly the same polytope. So we have some permutation variance in our vertex matrix representation. And also you can imagine if you acted on this vertex matrix with some GL2Z matrix, this essentially just corresponds to doing like a coordinate transformation on your lattice. So you potentially will get a polytope that looks very different, but it's isomorphic to the one you started with. So this is also equivalent. So we say that two polytopes, delta and delta prime, are equivalent if there exists a permutation matrix P and a GLNZ matrix G, where n is the dimension of your polytope, such that the two vertex matrices are related by this equation here. So when we generated data sets of reflexive polytopes, we wanted to know how many unique reflexive polytopes we had. So we wanted to remove all of this extra sources of redundancy. So the way we did this was computing the normal form of the polytope, and this essentially just picks a unique representative of the equivalence class. I won't go into the details of how you do this computation. The details are in the paper if you're interested, or if I can talk about it a bit later. So before I show you the results, I just want to explain to you the process by which we used a genetic algorithm to generate our data sets of reflexive polytopes. So the first thing we do is we randomly generate a population of bit lists, and then we evolve our population over several generations by going around that loop I showed you earlier. So ranking, selection, breeding, mutation. And then once you've evolved the population several times, we have a list of populations. And the next step is extracting any polytopes from these list of populations that correspond to reflexive polytopes. So any individuals that have a fitness score of 0. And then we remove the redundancy in this list by computing the normal forms and deleting any duplicates. And then this process is then repeated again with a new random population. So I will often refer to a run. So run means step 1 to step 4. So we repeat this process for several runs until we've generated all of our reflexive. So of course, we have a complete classification in 2, 3, and 4 dimensions. So in these cases, we stop our search when we've generated the known total number. But in 5 dimensions, where we only have this partial classification, we instead stop our search when we generate no new reflexive polytopes in 1,000 runs. So the total number will plateau. So any questions before I go into the results? Nope? Okay. So of course, it makes sense to start in the easiest case and work our way up. So starting in 2 dimensions, as I said, we have 16 reflexive polytopes, and the maximum number of vertices of these is 6. So we set our maximum number of vertices to be 6, and then we set min to be -3 and binary length to be 3, which defines our vertex coordinate range to be -3 to 4. And with this, we have an environment that captures all of our 16 reflexive polytopes. And this environment contains around 10 to the 11 states. So it's already a fairly large environment, even in the simplest case. But amazingly, just after a single run of the genetic algorithm, which takes a matter of a second on a standard laptop, we managed to generate all of the 16. And what I think is most impressive is that in the search, the genetic algorithm only visits a tiny fraction of the total environment to find all of the ones you're after. So this was a good start. And then we moved on to 3 dimensions. So now we have 4,319 of these polytopes. And this time, the maximum number of vertices is 14. And now we increase our vertex coordinate range by setting min to be -7 this time, and the binary length to be 4. So now we have a vertex coordinate range of -7 to 8. And now, again, we have an environment that captures all of our polytopes. This environment is much, much larger. We have a 10 to the 51 states this time. But amazingly, even in this very, very large and sparse environment, we still managed to find all of the reflexive polytopes. And this time it took around 100,000 runs. So this is considerably longer than the two-dimensional case, but it's still, the genetic algorithm is only visiting a tiny fraction of the environment.
So this looks extremely, efficient in the search, right? So do you have any geometric intuition behind it? Like, it seems that many of these reflexive polytopes seem to be related by some, not too much dramatic change, but
Yeah.
repeat a small process and then they are connected, and there could be some mathematics behind it.
I think it is interesting. The annoying thing about genetic algorithms is you don't really get any learned function at the end. So it's hard to really know. It's not really learning anything. It's not like a neural network that's learning a function. It's very much just a random process. I think the reason why the genetic algorithm is so amenable to these polytopes is it's a very discrete process. You're basically cutting up your data and sticking bits together. And because you can imagine cutting up a polytope, and if one part of the polytope is reflexive in the sense all of its hyperplanes are a distance 1, then that bit would be saved, and if it's added to another bit that's reflexive. So I think,
I see.
Yeah, the nature of polytopes with the nature of the genetic algorithms, they fit quite well together. But it's not really learning anything. It's just a very random process.
I see. Well, so in that respect, let's see. So genetic algorithm has been applied to many different type of problems. So if you take some canonical problem, whatever it is, with a similar size, etc., what is the typical efficiency? And is this the more efficient or less efficient than this?
I don't know. This is something I've considered actually, because I think for any problem, the sparsity of that we call them terminal states, like the good states for us, this is reflexive polytopes, the sparsity of terminal states within your environment, I reckon there's probably some standard sparsity that means that a genetic algorithm is going to succeed in finding them. And if it's too sparse, it won't do well. But I don't actually know. I haven't looked at other cases. But yeah, it's something interesting, I think.
Thank you.
Yeah. Yeah, so for 2, 3, and 4 dimensions, we know we found all of them because we compare to the existing data. Yeah. So in high dimensions, we know we found a reflexive polytope because it satisfies all the definition of being reflexive. We don't know that we found the true total number. We just know that we found a lower bound of the total number. Yeah, any other questions? Okay. So in 4 dimensions, as I said earlier, the complete classification of all these polytopes is around 500 million. So this is a very, very large number, and we didn't think it was worth us completely regenerating this entire data set. It would take a very long time to do so, and it already exists, so it's not really worth our time. So instead, we just focused on generating a small subset of these polytopes, and we chose to look at the ones with the smallest number of points. So this is where, in the fitness function, we had this term. Now we're turning on this third term, setting W3 to be 1, and we care about the number of points. And I should mention the reason why we look at the smallest number of points is because here the genetic algorithm will do much better. Because if you have a small number of points, you have a small number of maximal vertices, and you can constrain your vertex coordinate range to be much smaller because small polytopes tend to be quite compact around the origin. So you can constrain your environment, and so the sparsity of terminal states in the environment is going to be larger than if you were looking at larger polytopes, for example. So we focused on the 5 smallest possible numbers of points, which is 6 up to 10. So the second column is the total number of states in the environment. The third column is the total number of reflexive polytopes as taken from Hodge's data set. And then the fourth column is the number of runs it took our genetic algorithm to find this total number, and then the fraction of states visited during the search. So amazingly, even in the 4-dimensional case, for the small cases at least, we were able to generate complete data sets of these polytopes. What we really wanted to do was generate the 5-dimensional polytopes, because here, as I said, there's only a partial classification. So we had the opportunity of generating something new. And of course, the 5-dimensional polytopes will give rise to 4 complex dimensional Calabi-Yaus. So Calabi-Yau fourfolds are of course interesting in F-theory model building. So there's a physical motivation for this as well. So again, we focused on the 5 smallest numbers of points. So these total number of reflexive polytopes that we found, this time is not the true total number because there's no exhaustive database, but it's at least a very strong lower bound. So these are the total numbers we get where the genetic algorithm will plateau for 1,000 runs. And here is the number of runs it took to reach this total. So what we wanted to know was, yeah, amazing that we've managed to generate these 5-dimensional polytopes, but do any of these 5-dimensional polytopes give us new Calabi-Yau fourfolds? So yeah, I should mention that a reflexive polytope gives rise to an ambient toric Fano variety, and the Calabi-Yau varieties are the hypersurfaces in this ambient space. So in that sense, a reflexive polytope gives rise to a whole family of Calabi-Yau manifolds. And it can be the case that you have 2 different hypersurfaces from 2 different ambient spaces that actually are the same Calabi-Yau. So the space of all hypersurfaces of all of these toric varieties, they have redundancies in them. So the way to know whether you truly have a new Calabi-Yau is to compare the topological properties. And in the 3-fold case, there's a theorem by Wall that says that 2 Calabi-Yaus are defined by the Hodge numbers, the triple intersection numbers, and the second Chern class. So that's in the 3-fold case. I don't believe that this holds in the 4-fold case. However, if you do have 2 reflexive polytopes that give you Calabi-Yaus of 2 different Hodge numbers, then you know for sure that the Calabi-Yaus are different. So you can compute the Hodge numbers just from the polytope information. So this is a formula taken from Latterev's original paper, and there's similar ones for the other Hodge numbers as well. So here, L is the number of points, L star is the number of interior points. Of course, delta and delta star are your polytope and its dual, and then theta and theta star are faces of your polytope and faces of the dual. And I also noticed earlier that this should be a minus. That's a typo from my part. So if you stare at this formula for H11, you can see that if you wanted to have a small value for H11, you're going to want to have a small dual polytope, because you want this, well, this third term is always going to be smaller than the first term, and you want this first term and this last term to be small. But small polytopes is exactly what we generated with our genetic algorithm. So we thought, let's compute all of the dual polytopes of the ones that we generated and see which ones of the dual polytopes give rise to Calabi-Yaus with H11 equal to 1. And doing this, we found 15. So 7 of the 15 came from the 7-point data set, 8 of them came from the 8-point data set, and then no polytopes in all of these data sets gave rise to Hodge number H11 equal to 1. So we believe we found almost all, if not all, of the Calabi-Yau fourfolds from this toric construction that will give you H11 equal to 1. And then we compared these with Scarpa and Scholler's partial data set, and we found that, so Scarpa and Scholler's data set had 8 polytopes with H11 equal to 1. We found 15, and we checked that indeed there are 8, but also in our data set, and we found 7 new examples. So this is confirmation that we found new Calabi-Yau fourfolds with our genetic algorithm. So this is very, very exciting, but actually what I think is even more exciting is what we did next. So we thought, now, is it possible to specify what, say, Hodge numbers you want from your Calabi-Yau at the beginning and input this in as a term into the fitness function and use your genetic algorithm to generate Calabi-Yaus with a specific Hodge number? So we went looking into the literature for a physical motivation where someone was after Calabi-Yaus with a specific Hodge number. And we found this paper, and I have to admit, I can't remember exactly the details on it, but if anyone's interested, I can point you to the paper. But it gives a condition on a Calabi-Yau fourfold Euler number such that if you compactify 11-dimensional supergravity, you break n=1 to n=2 supersymmetry. So the condition is that the Euler number is divisible by 24, by 224, and 504. So we put this as a term into our fitness function. So now we don't care about the number of points. So we get rid of that third term we had earlier. And now we add in another third term, which essentially penalizes polytopes that give rise to Euler number not divisible by these numbers. And with this new fitness function, we then ran our genetic algorithm. And even after a few runs, so less than a minute on a standard laptop, we were finding examples that satisfy these constraints. So I think this is really, really the exciting bit. And if you take home anything from this talk, I want you to take home this, that machine learning has the capabilities of generating Calabi-Yau manifolds of a specific type. And this is very much a simple case. We just looked at Calabi-Yaus as constructions as hypersurfaces and toric varieties, and we just looked at constraining the Hodge numbers, but you can take this much further. So on that note, one of the things we're now looking at is the triangulations of the polytopes. As I said earlier, in general, a polytope will give rise to a singular ambient toric variety, and then the Calabi-Yau inherits the singularities of the ambient space. But you can take these so-called fine regular star triangulations and you resolve your singularities. So fine means that all of the points are included in the triangulation. Regular means, as this diagram is demonstrating, if you can obtain the triangulation by assigning a height to every point in the polytope, raising your polytope up one dimension with these heights, and then taking the convex hull and then projecting down the lower faces. And that's how you obtain your triangulation. And then star just means that the origin is included as a vertex in every simplex. So this is, of course, regular by its construction. It's also a fine triangulation because all of the points are included. It's not, however, a star triangulation because if you look at this simplex down here, it doesn't contain the origin as a vertex. So what we're looking at now is whether we can generate fine regular star triangulations of our genetic algorithms, because of course we would like a smooth Calabi-Yau, and also there are properties of your Calabi-Yau that depend on your triangulation. So as I said, Hodge numbers you can get just from your polytope. You don't need any triangulation, but there are other properties like the triple intersection numbers, for example, which do depend on your triangulation. So if we're successful in using our genetic algorithm to do these FRSTs, we can then combine this with the power of our previous genetic algorithm, and you can generate polytopes with more specific properties. And then just a note on some other applications. So one thing that Georgi, who's now working on this project with us, is looking at is, can we amend the fitness function to search also for elliptically fibered Calabi-Yau fourfolds, which is of course what we're after in F-theory. And this just puts a constraint on your polytope that it has a 2D reflexive polytope as a subpolytope. And then this second one is a more ambitious adventure, a project that I've recently been involved in, and I have to admit, I'm new to the world of axions, so I'm not an expert yet. But the idea is that we're looking at axions when you're compactifying type 2B on a Calabi-Yau orientifold, and the mass of your axions is dependent on your compactification, and axions can be candidates for fuzzy dark matter. And in that case, you want to have a low mass and a high decay constant. And both the mass and the decay constant depend on your compactification. So the idea is using also this genetic algorithm to search the space of Calabi-Yau orientifolds and the Kähler parameter to search for cases where you would have appropriate axial mass. And then another application is more of a pure mathematical application, is classifying other types of Fano polytopes. So these reflexive polytopes, as I said, give you Fano varieties with Gorenstein singularities, but there are other types of Fano polytopes defined slightly differently, which will give you other types of Fano varieties. And the classification of Fano varieties is interesting in its own right. So that's one thing I'm looking at as well. And then, yeah, genetic algorithms is the method that we chose to use for generating Calabi-Yaus, but this isn't to say that this is necessarily the best method, especially for other constructions of Calabi-Yaus. Say if you were dealing with sissies, for example, maybe the genetic algorithm approach wouldn't be the best thing to do. So I think it would be interesting to explore other methods. So reinforcement learning is a potential other method, and GANs is also something one could try. So there's, much scope for next steps. And I think that's all for me. So thank you very much for listening, and please ask me any more questions you have.
Okay, thank you. So we have plenty of time for discussions, but maybe before starting, could you explain what is it at the GitHub?
Oh yeah, I should mention the GitHub is the code. So it's written, I should put a warning out, it's written in C, but I'm currently working on a Python package with the people from CY Tools. So the Python package should be available in a couple of weeks. But if you want to try out the algorithm and you know how to work C, then please download the GitHub and play around.
I see. What about the data itself, the data of the polytope and things?
So the data itself is given in its vertex matrix.
Okay.
Yeah.
Great. Okay, then time for questions. Yes.
You mentioned these questions that start with the last one. That's the reason why
It's
right.
yeah. So if you're wanting to compute things like your Yukawa couplings of your compactification, you need not just the geometry, you need the metric. So in computing things like Yukawa couplings, you would need your metric, and it's a very well-known open problem. You can't construct an analytical version of the Ricci flat metric. So people have like numerical versions of doing this. And then machine learning, there are many avenues people are looking at. Some people are looking at just training a supervised machine learning algorithm based on data generated from the numerical methods. And I think other people are doing some other clever things like Ricci flow, for example, modeling a neural network as a Ricci flow. Yeah. Thanks.
Yes, please.
Mm-hmm. Yeah, that bit was really done by hand. So the genetic algorithm just generates polytopes, and then it's kind of like a side process of like, you generate these populations, you extract the polytopes, and then you save it in some list, and then you let the genetic algorithm run, and you're kind of just extracting. So yeah, the removing the redundancy by doing the normal form computation is kind of on the side. It's not actually in the genetic algorithm process. Yes. That is something that has been suggested to us, yeah, especially for like looking at ones like further than the H11 491 case is like, yeah, so that's one thing we want to try and do is looking at like the threefolds as like sub polytopes of the fourfold case. Yeah, I think that's something really interesting, and like looking at the tadpole constraint and looking at trying to break that bound. I think that would be interesting.
Okay. Other questions? Yeah, well, one question I have is that you mentioned the issue of triangulation, right? Discussing, exploring the triangulations. Now, I think there is already a program for doing that, like a TopCon or some other things. Do you know if there's you can connect the two things nicely, like
yeah,
as far as the interface of the data format is?
Yeah, so there's a few different algorithms for doing triangulations. Like you have TopCon, you have QHole, Quick, a few other algorithms, and like CY Tools is a Python package that you can basically use each algorithm you choose. But so these work, you can get like a complete list of triangulations for the small cases, for small polytopes. But if you're looking at say like the 491 polytope, you're not going to completely generate. And even I think those algorithms struggle in that case. So this genetic algorithm might be able to find triangulations there where the complete exhaustive algorithms would struggle. And also, I think the number of triangulations is estimated to be something like 10 to the 500. Like it's a very, very large number. So we're not planning on exhaustively generating triangulations. It's more just to generate.
So the purpose is different. So you need a different algorithm.
Yeah, like I think the existing algorithms for triangulations are good enough in the small cases, but in large polytopes like the 491, I think you can outperform them there.
Okay, great. Any other? Oh, yes.
Is there a reason why you need both reading and taking?
Yeah, so if you just had, is it this way? Yeah. If you just had the breeding and you didn't have the mutation, you'd probably just find one reflexive polytope, and then your whole population would just be that one reflexive polytope, and you wouldn't get any variation. So the mutation is just like making sure you're finding not just one case. I guess it's like in general, like evolution, right? You definitely need. You could do the process maybe with just mutation, but then mutation is just a random walk essentially in your environment, because mutation is completely random. So you need this selection and breeding bit to make sure you're taking the fit individuals, so you're not just randomly walking the state space. And then you also need the mutation to ensure that you're not just like honing in on one good case.
Okay, any other questions? Okay, if not, let's thank Elli again.